A very good morning to all the participants and our distinguished speaker. I welcome the wonderful audience for today's Talk 9 of webinar series on electron microscopy titled Transmission Electron Microscopy, Structure Analysis in both Material and Biological Science. I will begin with an overview of SAF IIT Bombay, which was inaugurated by our late ex-Prime Minister Shri Morarji Desai. Instrumental methods of analysis form an indispensable aspect of any research and development program. The Department of Science and Technology, DST, set up the Sophisticated Analytical Instruments Facility, SAF, in different parts of the country. The main objective of setting up these facilities was to provide guidance in acquisition of data using sophisticated instruments. Professor Anil Kotantarel is currently heading our CR&TS department. SAF IIT Bombay has several analytical instruments and provides measurement services to IIT Bombay users and to users from other colleges, universities, national laboratories, and various industries as well. The current slide shows the list of instruments funded by DST, in which 2 of the electron microscopes have been highlighted. The one at the bottom is an upcoming facility, a dual beam focused electron and ion beam, which will be installed soon. The next slide shows the list of instruments which come under the facility, central facility funded by IIT Bombay. Today, we are going to highlight the 3 transmission electron microscopes. One of them is a conventional TEM and the other 2 are field emission gun-based instruments with the different analytical capabilities. Like the 200 kV FEC-TEM has EDS attachment and can be operated at 120 kilovolts as well for soft samples. The 300 kV FEC-TEM has EDS and electron energy loss spectrometer with it. All are in-house at SAF CR&TS. We have created a LinkedIn account for SAF IIT Bombay. We would be happy to connect with you through this mode too. This is the brochure for the webinar series on electron microscopy, which is uploaded to this LinkedIn account. The following slide shows the staff at SAF CR&TS. We would be happy to welcome you to SAF and help you with the sample analysis. Talk 9 in the webinar series on electron microscopy is on transmission electron microscopy, structure analysis in both material and biological science, and it will be given shortly by Dr. Tetsuo Oikawa. It's a great pleasure for me to welcome Dr. Tetsuo Oikawa, who is a Senior Product Manager for TEM JEOL Asia Private Limited, based in Singapore since 2013. He pursued his postgraduate course from Kogakuin University in 1980, and then he joined Electron Optics Division of JEOL Limited. He was an invited professor at the University of Paris for 8 years. From 2007 to 2011, he had been the director for European Application Group JEOL Europe. We are sure that this talk will enlighten the knowledge of the upcoming researchers in the field of electron microscopy and encourage them to use the electron microscopes. Questions and answers to be posted in the question and answer box. Question and with participant's name only will be answered. So let us commence today's webinar. Over to you, Dr. Tetsuo Oikawa.
Ladies and gentlemen, thank you very much for great introduction. Today, I'd like to serve as the basic knowledge on transmission electron microscopy, mainly focusing the structure analysis. Okay. As this is just a flow of the operation as transmission microscope like this here. Okay. Then, in order to observe and collect the data, we have to prepare the sample of specimen here like this. So sample preparation also very important. And after sample preparation completed, we can install the sample to microscope. Then we can observe this kind of example is an atomic image and something. After that, we have to make a data analysis, such as a diffraction analysis or lattice spacing measurement like this. Today's lecture has just introduced the knowledge of transmission microscope at first, at basic operation and which kind of operation technique available for material science and also biological science. Then data analysis, such as the diffraction analysis and measurement of the spacing. Example, I'd like to introduce the examples. And also finally, I'd like to introduce the some of the specimen preparation technique as like this. Okay, so there's a many kind of sample preparation technique. Today time is limited. Only 2 examples will be introduced. Okay, as this is today's subject. First one, I'd like to introduce the basic principle of transmission microscope and data collection, material science, and for biological science. And also data analysis. I'd like to example introduced only 3 for high resolution TEM imaging analysis, and also diffraction analysis, and also 3-dimensional morphological structure observation in biological sample here like this. Then other specimen preparation technique, crushing technique, and ion slicer technique will be introduced. Okay, first one, I'd like just to introduce basic knowledge of transmission microscope. As transmission microscope was developed in 1931 by Professor Ruska. It was a big contribution. Then he was given a Nobel Prize in physics in 1986 for this development of a transmission microscope. It was a prototype of a transmission microscope he developed. And also in JEOL, transmission microscope company, first product DA1 was developed 1947, long ago. JEOL developed the transmission microscope technologies after now consistently over 70 years like this until today. Okay. So now this is just a principle of transmission microscope. Why the electron can be used for a transmission microscope. As you know, electron is a charged particle, but electron can be accelerated with applying the voltage, positive voltage, because electron is negatively charged in the vacuum environment. In order to landing the electron, vacuum environment necessary, then electron landing toward the anode. In this phenomena, wave generate as like this. Okay, electron momentum, landing electron, and wave generation, both phenomena simultaneously exist. Do not confuse. Electron never change to wave. Electron still exists, can arrive to anode with momentum. Simultaneously, electron wave generate. We can apply this electron wave as a electron diffraction, electron wave optics, and image forming. And also simultaneously, this electron momentum can be excited the specimen. We can observe the X-ray excited from the specimen or electron energy loss spectrum from this specimen excited. We can observe the image of wave image, morphological image, and also specimen information simultaneously. This wave proposed by Broglie, so we call this a Broglie wave or material wave like this. Okay, As the wave has a wavelength, electron wave normally, in case of a 100 kV accelerating voltage, 0.0037 and 200 kV 0.0025 nanometer. The wavelength huge small as comparing with the light wave as like this. Light wave is a few hundred nanometer order depending on the color like this. Owing to this short wavelengths, electron microscope offer the very high resolution imaging. Okay, as electron trajectory can be changed by applying the magnetic field because electron is a negatively charged. Then, for example, magnetic flux applied, electron can be changed direction due to the magnetic force. We call this a Lorentz force. Then, lens of electron microscope is apply the magnetic lens. As round field of magnet is applied, upper N pole, bottom S pole, magnetic flux distributed on the way to the electron trajectory. Electron direction can be changed by this magnetic field. This phenomena is exactly equivalent as light to glass lens like this. The focusing function is exactly same as equivalent. So it is very easy to understanding. So the optical microscope is very familiar for us. Then as comparing the principle with left hand is the optical microscope, right hand in the transmission electron microscope. You can see a source is light in light microscope and condenser lens, glass lens, and also objective lens. The specimen is very thin. Light should be transmitted the light image focused by objective lens and magnified by projector lens. It was projected on the screen. As in the electron microscope, source is not a light, but the electron gun. Electron generated and condenser lens collects the electron beam. This lens is not a glass, but a magnetic lens. Then specimen also same as optical microscope should be very thin. Electron should be transmitted. Transmitted the electron image was focused by objective lens of magnetic field. Then again magnified projector lens and image was projected on fluorescent screen because electron light cannot be seen. It's not visible. Then intensity of electron image was transferred by fluorescent screen into visible light. We can observe the transferred intensity on fluorescent screen. So principle is the exact same, only the difference is electron instead of light, but lens instead of glass, but magnetic lens like this. Okay, the appearance of the electron microscope is like this. There is the big microscope column. Top of the column, here is the electron source, electron gun, and also objective lens, projector lens, and also image screen. Okay, inside of the column, keep vacuum in order to running the electron, and also magnetic coil, magnetic lens is filled in the column. Both side operation panels like this. Okay, approximately the performance is magnification about maximum 1.5 million times or sometimes 2 million times magnification possible. Resolution depending on the instrument and model, but 0.2 nanometer order resolution possible. As you can imagine, the single atom diameter is approximately 0.3 nanometer. Resolution is much higher than single atom. Then we can observe the single atom image by electron microscope. Okay, the principle is like this: the illuminating the specimen with visible instead of visible light, but electron light, and also lens instead of glass lens, but electromagnetic lens. Okay, so And electron microscope offered many kinds of information. First one, this is a typical function of a microscope. We can observe the morphology of the specimen. We can measure the size or structure or shape. So we can make a structure analysis, such as the atomic arrangement or crystal structures of specimen. Also, simultaneously, we can make an elemental analysis of the specimen, and also it is the local information. Observing the high-resolution image, simultaneously, we can select the local information of the element. And also, we can make a measurement of electron potential, specimen potential, such as a magnetic field or electrostatic potential can be observed. So electron microscope offers many kinds of information from the specimen like this. Okay, I'd like to just introduce the image formation and how to make an image in the electron microscope. As principle is similar as optical microscope. In this figure, the lens, objective lens here, illustrated as a glass lens. Practically, lens is magnetic field. But as mentioned before, electron lens focusing function is equivalent to the optical lens, then illustrate by glass lens as like this. This is the specimen. Specimen should be very thin. The incident, this electron, not the visible light. Electron should be passing through the specimen. Then transmitted electron can be focused by objective lens. Finally, image projected on the projected screen like this. Imagine this height of the shape is corresponding to the intensity of image. As electron passing vacuum, no specimen here, no absorption by the specimen, higher intensity can be arrived on the screen here. But if electron passing the thick area, some of the electron absorbed in the specimen, the intensity reduced, image go to dark. As like this, thinner position becomes bright contrast, thicker area becoming dark contrast. We call this absorption contrast. Okay? It is very similar as optical microscope. And also, if the specimen has some of the crystal, electron scattering is generated by Broglie reflection. So scattered electron can make the diffraction spot off-axis position in the backfocal plane of the objective lens. When we can combine the small diameter of objective aperture, scattered electron can be cut. Then intensity cannot arrive to the image plane. It is same as absorbed intensity. Then we can generate the scattered electron contrast. We call this is a diffraction contrast. As like this, absorption scattering intensity can make an amplitude contrast, amplitude imaging like this. This principle quite equivalent to optical microscope like this. Very simple. In morphological observation, this image forming is very effective. On the other hand, sometimes we can observe very high resolution atomic imaging. So in this condition, we can make a scattered electron diffraction spot can be accepted for image forming with a big diameter of objective aperture combined. Scattered electron has a different position as optical axis. Then, due to the distance, generate a phase difference. Then transmitted electron, center beam, and the scattered electron has overlap and generate the phase interference fringes due to the phase shift. Then we can observe this kind of interference fringes. We call this contrast is a phase contrast. This phase shift is corresponding to the scattering angle of crystal here. Okay, as higher scattering angle generate a higher phase shift. As mathematically, this interference fringe of the image plane is corresponding the atomic lattice imaging of this scattering crystal here like this. It was a Fourier transformation of the image potential to backfocal plane. Again, once more, the Fourier transformation come back to the image on the image plane like this. As we can observe, the atomic arrangement or lattice spacing arrangement can be observed, this phase contrast. There are the two kinds of image contrast as like this. Okay, for example, this is a lower magnification imaging at biological sample. Then objective aperture installed, little bit smaller objective aperture, little bit bigger objective aperture, 120 micrometer, contrast 13%. And also smaller objective aperture employed, 20 micrometer, contrast enhanced 24% as like this. So changing the objective aperture diameter, contrast change. So if you need a more higher contrast imaging, we recommend use a small objective aperture like this. And also, magnified image was also magnified again by intermediate lens system and projector lens system. Specimen is here, and first stage of imaging of objective lens here. This is objective lens. Again, this illustration lens is illustrated by the glass lens, but practically it was a magnetic lens. But the first stage of objective lens is once again magnified with the first intermediate, second intermediate, and third intermediate, finally projector lens. Each lens has a 10 times magnification, and projector lens has a 200 times magnification. Finally, we can observe the 1 million times magnification very easily. But as magnetic lens, focal length can be changeable by changing the lens magnetic flux excitation current. So we can easily change the focal length of the magnetic lens. We can change the magnification very easily. Then very low magnification also possible with long focal length. Sometimes objective lens turn off. Instead of objective lens, we can employ the long focal length of objective mini lens. Finally, you can observe the very low magnification, such as the 10 times, 20 times, 50 times magnification, same as an optical microscope. And also, changing the focal length of first intermediate lens from image plane of objective lens to backfocal plane of objective lens. There's an electron diffraction pattern formed on the backfocal plane. In this situation, we can observe the electron diffraction pattern in the final image plane like this. Electron diffraction pattern is the first stage of Fourier transformation of the structure image. This is similar as X-ray diffraction, but by electron. We can observe the crystal structure by electron diffraction like this. As switching the focal length of intermediate lens here, image plane to backfocal plane, we can observe the two-dimensional image in the image mode and diffraction pattern in reciprocal information of the specimen simultaneously. The electron microscope offers much information as like this. Okay, this is just an example of low magnification. Magnification was only 50 times magnification. Specimen was distributed the metal grid like this. The diameter of the grid is 3 millimeter. Inside the effective area is 2 millimeter as handling the specimen holder. So there is a metal grid like this. Then specimen should be sliced as thin, then distributed on this metal grid. We can observe the inside of window of the metal as like this. Okay. This is an example of a biological sample sliced by the ultramicrotome. Okay. This is an example of higher magnification observation in biological section, specimen with the small intestine of rat. Left hand was about 10,000 times magnification. We can clearly observe the inside of the small intestine microvilli structure, and this area magnified about 40,000 times magnification here. A small intestine microvilli structure can be clearly observed. This microvilli absorbed as food as like this. An example of the high resolution imaging. This is a gold thin film in atomic image in high resolution condition. We can observe this white, each small white disk corresponds to a single atom, atomic image. You can see here 5 nanometer scale marker is here like this. Sorry. Then atom to atom distance is about 0.2 nanometer order, as depending on the structure here. And also we can observe the dislocation in high resolution imaging here. This is a single phase and second phase, another phase, phase 2 phase. Here the atomic dislocation, atomic arrangement can be observed as clearly. This is high resolution phase contrast atomic imaging. Okay, as like this, electron microscope applicable for many kind of application field, such as ceramics, catalysis, carbon material, energy and battery material, and metal, semiconductors, biology and medical science, and also chemical and polymer sciences like this. So today I'd like to introduce some of the example of application data. Okay, so now just I'd like to introduce the example of material science. This is an example of ceramics. Okay, specimen was a silicon nitride. Okay, so relatively lower magnification of hexagonal silicon nitride. Electron beam orientation is 001 orientation incident. Hexagonal structure is clearly observed, but this area is magnified. You can see this atomic resolution. This hexagonal structure corresponding the atomic location of silicon. This dark spot corresponding the single atom silicon. Here, this green corresponding the location of the silicon as atomic model like this. Beside of the silicon, there is the light element of nitrogen, but unfortunately, nitrogen cannot resolve in this image. But the silicon atom is clearly resolved as a single image like this. This is a performance of transmission electron microscope. And also this example of carbon material. Single-walled carbon nanotube is clearly observed like this. As carbon material is beam sensitive, so in order to avoid the beam damage, accelerating voltage was reduced lower to 120 kV, changing the voltage like this. And also next one, example biology. This is a coronavirus example. Coronavirus a little bit small, as 100 nanometer diameter order like this. But this data, as electron microscope, original data is only black and white because of the intensity of the electron intensity. This color is a shadow color painted by artificial. So color is a no physical meaning, only for presentation. But we can clearly observe the structure of coronavirus clearly as like this. The data was obtained at a magnification of 50,000 times magnification. And another example of biological section, specimen was a frog retina. Specimen was sliced by ultramicrotome, then magnified and observed 10,000 times magnification. You can observe the structure clearly as like this. This is an example of biological data collection. Okay, as in the illumination condition for condenser lens, we can make many kind of beam condition, parallel beam excitation, and small probe and focused beam. For example, we can make a small probe focused on the specimen. diameter is about 0.2 or 0.3 nanometer order small probe can be focused on the specimen. Then we can make a diffraction. We call the nano-beam electron diffraction possible. This is just an example of nano-beam electron diffraction technique. Specimen was a part of the semiconductor here. This is a lower magnification observation. This interface was magnified here. Silicon single crystal, and also outside is amorphous area. The beam diameter is about 5 nanometer of the beam condition as comparing 10 nanometer scale marker here. This amorphous area selected, electron diffraction make a hollow, meaning amorphous, no structure. As yellow position here, this crystal, the silicon single crystal, and pink area, different orientation of single crystals, as like this. Okay, as selected area is selected much field of view as green like this. All the information overlapped, but nano-beam diffraction can select small limited area and information can be clearly observed as like this. Now for the structure analysis, nano-beam diffraction is very effective as like this. And also another technique as like this, it's a scanning transmission microscopy. Not only the beam expanded broad, but electron beam focused small probe diameter on specimen. It is similar to the scanning microscope. Then beam is scanning two-dimensional on the specimen, but transmitted electron can be detected. We call this is a transmission, but the scanning transmission image. Simultaneously, we can observe the X-ray generated this small area can be X-ray detector, and also electron energy loss spectroscopy can be applied. Okay, then as scanning transmission microscope image, STEM image, bright field image, and scattered electron, high angle dark field imaging, heavy element of specimen such as the platinum distributed on the zeolite here. Heavy element of platinum generate a lot of scattered electron, then contrast become white as like this. As comparing the 20 nanometer scale marker here, this small particle almost less than 1 nanometer. Small particle of platinum can be clearly observed as white contrast. This is the reason why this STEM dark field imaging is very effective to observe heavy element of catalysis as like this. And also another example, a catalysis example here, a gold particle was distributed on the titanium oxide. Here, gold particle, dark spot in bright field, but white spot in dark field imaging. It's very clear. And also this STEM image can be applied for also biological application. Upper is the STEM dark field image of kidney of rat. We can observe the very high contrast imaging as scattered electron. Lower is a conventional transmission microscope, bright field imaging. As comparing the both image, we can collect much information of the structure of the specimen like this. And also a combination with X-ray detector as like this. Because incident electron has a momentum, this energy can excite the electron of the specimen. Then a characteristic X-ray can be generated like this. Characteristic energy is a specific energy depending on the element. As collecting the characteristic X-ray by X-ray spectrometer, we can make an X-ray spectrum, and according to the energy of the X-ray spectrum, we can identify the element, including the specimen. As probe diameter is very small, at nanometer order, we can focus the beam on the small area. We can make an elemental analysis of the specimen. As an example here, this is a small particle, boron nitride, distributed on the carbon film. Okay? Then beam was focused about the 10 nanometer or 10 or 20 nanometer beam condition from boron nitride signal crystal. Signal obtained boron signal, carbon from the background, and nitrogen from boron nitride. oxygen is absorbed from gas on the carbon film, as like this boron, carbon, nitrogen, oxygen. Nearest light element can be clearly detected as like. We can identify boron nitride image. As simultaneously scanning image of this scanning transmission image here. Okay. Yeah, this is the transmission image of catalysis. Simultaneously, we can observe the scattered, high-angle scattered dark field image. The specimen was a gold and palladium core cell structure nanoparticle. Particle diameter about a 50 nanometer order. Then scanning and simultaneously we can collect the gold characteristic X-ray, palladium, and also gold palladium overlapped here. We can identify the core cell structure inside gold, outside palladium, like this. It was obtained just 5 minutes due to the higher sensitivity of X-ray detectors like this. We can make a higher resolution imaging simultaneously, small area elemental analysis with high throughput like this. And also, electron beam has a higher coherency. We can make a higher coherent electron holography. And the specimen is here. The electron transmitted the specimen had a potential modulation. The other side transmitted in the vacuum, no modulation. So both the electron wave has an interference fringe, so-called the electron hologram. Then this hologram has this potential information. As after phase reconstruction, we can make a potential distribution. In this condition, specimen was a magnetic field. This potential, phase potential corresponding the magnetic flux as like this. Then as like this, if the specimen has a magnetic domain, magnetic flux, we can observe the magnetic flux distribution on the specimen. As in case of the permanent magnet, it's iron, copper, niobium, silicon, boron, very strong permanent magnet. Upper 2 is a Lorentz microscopy. You can observe, this is the TEM observation with Lorentz condition. We can observe the magnetic domain as black and white contrast. Lower is this hologram, right hand phase reconstructed the magnetic flux distribution. You can clearly observe the magnetic flux change as the magnetic domain as like this. As like this, electron beam can offer the potential distribution analysis from the specimen like this. And as the specimen of transmission microscope is very thin and image was 2D projected, it was a kind of disadvantage of transmission microscope because depth information cannot observe. Then recently, electron tomography technique was developed. Principle is the same as X-ray tomography, observing the specimen with different direction of specimen. That's the meaning. The goniometer of the transmission microscope can be controlled. We can observe the many kind of projected image, many kind of direction of projected image. After that, as according to the mathematical support, we can reconstruct this three-dimensional information. As goniometer function from 0 degree and up to 90 degree, we can tilt the goniometer stage. I can show the mechanical tilting function as like this. This is an example of biological sample. This is a tilting axis. Specimen is tilting very smooth. Mechanical control is very smooth. Okay. Then, as example of 3D observation with copper nanoparticle. This is only 2D projected image. It looks small particle, but as after reconstructed, you can see this is the real shape of the particle. It was not a particle, but a rod as like this. Data was obtained plus minus 65 degree with 1 degree step as like this. As like this, in order to understanding the real shape of the specimen, 3D information observation is very important. As also in the case of the polymer example, it is block polymer. This polymer has a network structure of the inside. This two-dimensional two independent network structure can be well reconstructed in the tomography observation like this. Okay. Those are example of data collection. Then I'd like just to introduce the high resolution TEM image analysis. This is just an example of high resolution imaging like this. Then just we can try to the Fourier transformation like this. So these are these spacing corresponding depending on the lattice spacing, and also interface generate a broad scattering as streak like this. Then selecting the specific intensity like this, we can select the specific lattice, only this lattice and only another lattice here. We can clearly observe the interface grain boundary as clearly like this. As selecting the another lattice here, lattice is modulated like this. So this is a kind of high resolution lattice spacing analysis with using a 2D filter, 2D Fourier transformation special frequency filtering application. As like this, as looking for the image, we can only observe just a shape, but comparing with the Fourier transformation, we can clearly identify the interface of the boundary as clearly like this. Okay. Also, another electron diffraction analysis like this. This is an example of organic material. Specimen was L-histidine. L-histidine is, we are very familiar to L-histidine as a food or medicine, but a crystal is a very higher beam sensitivity. We can make a nano-beam diffraction from this crystal image. Then we make a crystal structure analysis by electron diffraction pattern. This diffraction pattern was observed, this crystalline with many kind of direction, then identify the d-spacing and mirror index like this. We can identify the structure. There are the two kind of typical model, the L-histidine A type, L-histidine B type. First, it was no way to identify A type or B type, but only in this technique we can identify the d-spacing with electron diffraction pattern. Then we can identify comparing the A-type model, B-type model diffraction, measure the intensity here, as this measured one is a good agreement with A-type model. So we can understanding this L-histidine was crystal A-type pattern, not the B-type like this. So as like this, owing to the electron diffraction pattern analysis, we can identify the crystal structure as like this. Okay, as comparing the this is the X-ray diffraction spot. We can observe the same information from electron diffraction pattern as like this is the reconstructed image here, like this. As comparing the X-ray diffraction, as X-ray diffraction has all the d-spacing, but electron diffraction information is limited due to the incident electron beam direction. Okay, excited the plane is limited, but we can identify the same plane as like this. Okay, another example is a biological. So data was obtained from the T4 phage and cryo embedded. So the T4 phage was rapid frozen embedded in the amorphous ice, then apply the tomography, electron tomography technique and reconstructed. We can observe the almost live environmental T4 phage or biological example can be reconstructed as like this. Okay, as summarize, the advantage of a transmission microscope as like this. We can make a high resolution imaging. Resolution is now approximately 0.1 nanometer order. That's 1 angstrom order. And elemental analysis possible is a small area. Approximately 1 nanometer order area is possible. And also, a combination with the electron tomography technique, newly developed technique, we can observe the three-dimensional information. Not only two-dimensional projected, but the three-dimensional depth information can be also available. Okay, now I'd like to introduce the specimen preparation technique shortly. As there are the many kinds of specimen technique, and depending on the specimen and some specific instrument is like this. Target of the specimen preparation is we have to make a very thin sample. How thin is? Ideal thin, meaning a single atom. But practically, as a penetration power of electron, practically up to 100 to 200 nanometer of the thickness in 200 kb or 300 kb microscope. So, as first one, crushing. Crushing is very easy. Crushing, such as applied with catalysis or ceramics, or sometimes fibers. And ion milling, ion beam bombard the specimen. Then specimen is polished by ion beam. Okay. And also polishing using the chemical to metal or alloy, and also chemical polishing also, such as for semiconductor, and also focused ion beam. And this technique is very advanced technology, but small focused beam can fabricate the specimen itself. It's applicable for metal, ceramics, semiconductor. Recently, it is now expanded to the biological application. And also microtome. This microtome can mainly apply to, biological, but also polymer slicing. Okay. Today, I'd like to introduce just an example of crushing and ion milling as like this. Crushing is very simple. Powder should be crushed. It's mortar as like this. This small powder is solvent such as ethanol and also this kind of alcohol, then distributed on the specimen. For example, L-histidine, I already introduced the diffraction analysis. The single crystal of the sample is like this. It was crushed by mortar like this. This powder can be distributed on this grid. This is a TEM standard grid. Okay, diameter 3 millimeter metal. There's many kinds of metal, such as elemental analysis, copper, nickel, molybdenum, or something such as gold. Then biological section can be distributed on directly. But if powder is very small, we can distribute it the carbon microgrid and also sometimes very thin carbon film. Then sample, a small powder of sample distributed the carbon microgrid, we can observe this particle in the high magnification. And also if sample is a little bit bigger, the microgrid not necessary, but we can observe carbon film not necessary, but we can distribute the crystal as like this. Okay. And also ion milling is like this, specimen milling the ion, but today I just introduced ion slicer. As this is the appearance of the ion slicer instrument, as specimen is prepared as about the length of 3 millimeter, thickness 0.1 nanometer order. Inside of this instrument, here is a protection belt. Then upper, there is an ion source tilting. Then ion beam is irradiated according to this shadow of the shadow belt. Here the small hole can be obtained. As like this cross-sectional observation, original section sample, ion beam irradiate, thinning, and we can make this knife edge thinner area as whole. We can observe the field of view as around the hole like this. Then finally, we can observe this film as supported the diameter 3 millimeter grid here, because the specimen holder is limited at the 3 millimeter. Then small hole is fabricated as a layer structure, such as the sectioned sample for semiconductor. Then we can observe the sectioned long field of view as the semiconductor example here. As magnified here, we can observe the semiconductor structure at the thin uniform thickness as processed the ion beam slicing like this. This is one of the example of ion beam fabrication. Okay. Then magnify the image, TEM image, and magnified here, we can observe high resolution imaging like this. This ion slicing is one of the powerful technique for specimen application for material science. Okay, as now today I'd like to summarize. I introduced the basic knowledge of transmission microscope, basic principle. Okay, so electron wave, and also data collection, material science, and also biological science, and the image processing of high resolution TEM imaging, Fourier transformation filter, and diffraction analysis, and tomography in biological cryo sample. And data, two of the example of data preparation is introduced. Okay, thank you for your attention. But I already received many questions, about 37 questions, but time is limited. Now I'd like just to introduce the answer for the question. The question is, can you perform TEM under high pressure and low temperature? We are interested. What is the instrument limitation? Okay, combination with environmental specimen holder. This holder has both sides, upper, lower, is a very thin film, such as made of silicon nitride. We can feel the gas inside of this film. The gas pressure up to 1 atom, 1 kilopascal, also possible. We can feel the gas such as the nitrogen, hydrogen, oxygen. Many kinds of gas flow can be applicable. We can observe the specimen interaction with the gas. Gas reaction can be observed on the specimen. And also combination with the cooling holder. Mainly, we can apply the liquid nitrogen cooling holder. We can reduce the temperature lower to liquid nitrogen temperature. If for special application, liquid helium temperature cooling holder can be also available. So we can observe as like this combination with a special holder, high pressure holder, or a cooling holder, and also heating also available. If apply the heating holder up to 1000 degree of heating is also available. As like this combination with many kind of functional holders, we can change the specimen environment in the microscope. Okay, and the second question is, I like to know the lattice spacing measurement in TEM. And also another one more question, you want to make a measurement of D-spacing of electron imaging, and also compare the XRT. I just introduce the example of analysis. Let me see. Maybe, okay, let me see. Then as like this data was measured with the Gatan digital micrograph. As like this, you can see that this spacing measurement as like this. This is just example of measurement function or intensity profile as like this. For example, this one, eh? Okay, as like this. Then as just change the pixel number as a little bit wider pixel number. You can see here, atom to atom distance can be measured at also 2 nanometers like this. Okay, but as in the TEM magnification, magnification error is included about a plus minus 5%. If you need a more precision measurement, you need make a calibration of the magnification using the standard sample. And also as like this process, if you apply the Fourier transform, if you make a Fourier transformation as like this process, here you can make a FFT filters like this, and also you can make a despacing measurement as like this. For example, here this corresponded to 2 nanometer order like this, as you can see, and the different despacing as much higher than or more here like this. We can measure the reciprocal information as like this. So TEM offer the length information as two-dimensional condition, but important is the error is included in the magnification. We have to make a calibration at first using the standard sample. Okay, as the time is already limited, so I'd like to, if you have some question, I'd like to accept the 1 or 2 questions depending on the time.
Thank you, Dr. Tetsuo Oikawa.
Thank you.
Let's begin with today's question and answer round. Okay. Can we 100% stabilize the metabolism process of any live tissue before viewing in TEM?
Okay, and live tissue, in example, the biological or polymer science, some of the limitation of the microscope observation is specimen is very beam sensitive. As electron microscope using electron beam has a very much momentum. The energy is very high. Then observing the specimen simultaneously breaking the specimen. So polymer or biology has a very sensitive for electron energy. Then we cannot make a more detailed analysis by electron beam. Only low magnification observation or shape observation. If we try the more detailed high magnification observation, due to the strong electron emission, specimen broken. So in order to reduce this specimen damage, one technique is a cryomicroscopy, but still intensity is limited. Okay, most big limitation of the transmission microscope is a specimen damage. Okay. As introduced today, elemental analysis is mainly for material science, such as silicon or catalysis. Those are fortunately very stable for electron beam excitation. Then we can make a good information of elemental information, but it is difficult to apply biological or polymer science due to the damage. Okay.
Okay. Yeah, thank you.
Thank you.
Another interesting question is how to prepare the samples for cross-sectional TEM observations.
Okay, as introduced today, one is the ion slicer using the ion beam section, and also if sample is not so hard material, ultramicrotome also applicable. Okay, not only biological sample, some semiconductor or soft material, soft metal can be slicing by the ultramicrotome, also applicable. Okay.
Okay, thank you. The next question is the basic handling of biological samples and also organic samples. What are the stains that can be used for better resolution imaging?
As mentioned previous question, due to the beam sensitive material of the polymer or organic material, so high resolution imaging is now limited. Okay. If we can try to the high resolution imaging, we have to induce a much strong electron beam, then specimen broken. This is the limitation.
Fine. Another question is it possible to get to know about the percentage of crystallinity through SAED pattern analysis?
Once again, please. Sorry.
Is it possible to get to know about the percentage of crystallinity through SAED pattern analysis?
Crystallography?
Yeah, percentage of crystallinity.
Okay. So the definition of crystallography is very difficult, but observing the selected area diffraction, as introduced today, use the Fourier transformation. Crystal offer the diffraction spot then selecting the diffraction spot, and amorphous is the hollow ring. So compare the intensity of diffraction spot of crystal and hollow ring. You can calculate the crystallography of the concentration. Okay. Mainly in this work, I recommend the electron diffraction not using the electron image, because electron image included the aberration, as mentioned before, lens aberration, and also background intensity. But electron diffraction does not suffer the aberration. So electron diffraction is a much precision diffraction intensity from the specimen. Okay.
Thank you. On behalf of CEF-CRNTS, I would like to thank Dr. Tetsuo Oikawa for an interesting talk on transmission electron microscopy, structure analysis in both material and biological science. We are really grateful to Dr. Tetsuo Oikawa for answering the questions. I would also like to thank our head, Professor Anil Kotantarail, for his continued support in this webinar series. And last but not the least, I thank all the participants for attending this webinar and making this event successful. A link for the feedback form is shared in the question and answer section. Please fill the form. Your valuable inputs are important to us. The registration link for the next webinar is now open on our website. The upcoming talk is on advances in EELS instrumentation and analysis, high-speed spectroscopy with extended energy and dynamic range by Dr. Paolo Longo. I request you all to join us for our next talk. Once again, thank you all for making the webinar series a successful. Stay healthy and safe. Jai Hind.